Welcome to the deep dive. Today, we're plunging into a specific research paper. It's one that really tries to tackle a tough problem in conservation. Yeah, how do you manage biological threats when, well, human behavior is a huge part of the picture? We are specifically diving into risk and non-indigenous species management. The lead author is David Finnoff, along with Jason Shogren, Brian Leung, and David Lodge. It's pretty dense research. It really is. It brings together ecology and economics, these two worlds that don't always talk to each other perfectly. So our mission today is basically to unpack it for you. We want to distill the core findings so you understand what they figured out and, importantly, why it matters for managing resources really anywhere.
And it's such a timely deep dive. We're talking about non-indigenous species, NIS, things like invasive plants, zebra mussels, you name it. We know from researchers like Elton and Kareva that they're a major cause of biodiversity loss, environmental damage. The costs are just huge. The real challenge, though, isn't just recognizing the problem, is figuring out how to manage these threats cost-effectively. You can't just throw infinite money at it. So you need a solid framework, one that actually considers the biology of the invasion and the economics of the people trying to manage it.
And that's really the innovation here, isn't it? This paper doesn't just look at, say, how fast an invasive weed spreads. It models how our choices, how we spend money, where we put our effort can actually speed up or slow down that spread. They've built this unified framework using population ecology and economic theory. Okay, so let's start with the big economic idea they lean on, this concept of endogenous risk. What does that actually mean?
Right, endogenous risk. It's kind of the bedrock of their whole approach. So traditionally, risk management often uses what's called a damage function. It basically treats the risk, like an invasive species arriving, as something external. Like a hurricane, you know it's coming, you just react. But endogenous risk theory says, hold on, people and managers actually influence the level of risk they face. It depends on the effort they put in, the investments they make, their behavior.
So it's not just something that happens to us. We have a hand in creating the level of risk we're exposed to.
Exactly. Your choices change the odds. You're not just reacting, you're actively choosing your exposure.
Okay, so if our choices shape the risk, how does the economic theory in the paper break down the types of choices we can make when facing something like an invasion?
Good question. So economically, the responses generally fall into two main categories when you're dealing with this kind of endogenous risk. First, you've got what they call self-protection or prevention. These are the proactive things you do. Efforts to reduce the likelihood that the invasion happens in the first place.
Like inspecting cargo ships for invasive species or maybe setting up early warning systems?
Precisely. Things like ballast water regulations fit in there too. It's all about stopping it before it starts or at least catching it really early. Then the second category is self-insurance or adaptation, which they often call control in this context. Here, you're basically accepting the invasion has occurred or might occur, and you're trying to reduce the severity of the damage when it does hit, lessening the blow, essentially.
So damage limitation. Okay, the paper uses the zebra mussel, Dreissena polymorpha, as its main case study. That seems like a perfect example of this tension. I mean, these things clog up water intake pipes for cities, for power plants. The economic damage is immediate and really obvious.
It's incredibly costly. Researchers like Pimentel estimated, I think a while back now, but still indicative, that zebra mussels cost U.S. industries something like U.S. $100 million per year. And that's mostly just in control costs.
Wow, just control.
Yeah, and that's the fascinating part in the real world. Most of the money spent is on control. Physically scraping mussels off pipes, flushing systems with chlorine, reactive stuff. This is happening even while the species is still actively spreading to new lakes and rivers. The amount spent on prevention is often tiny in comparison.
So we're mostly paying for cleanup, not prevention. That really highlights the trade-off this paper is trying to model dynamically over time.
Exactly. Which strategy is better? Or, more realistically, what's the optimal mix of prevention and control, and how does that change based on the situation?
Okay, so to model this dynamic trade-off, the paper sets up a scenario. It has two main decision makers acting at the same time, right? You've got the private individuals or firms, the ones feeling the direct economic pain.
Right, like the factory owner whose pipes are getting clogged.
And then you have the benevolent manager who represents the public interest, sort of the policymaker looking at the bigger, longer-term picture.
That's the core setup. And they have different perspectives and different tools. The firm, the model assumes, is pretty myopic, meaning they have a high discount rate, they care a lot more about costs and profits today compared to 5 or 10 years down the line. They see the mussels that are here right now, and they just want to minimize the current damage.
So what can the firm actually do in the model?
Their choices are private and immediate. They can use adaptation, maybe running their cooling systems longer to compensate for reduced water flow. That just deals with the consequence. Or they can use private control, like flushing their own intake system with chlorine to kill the mussels locally. It's about reducing the damages they personally experience right now.
Okay, focused on the here and now and the public manager.
The manager is playing the long game. They look at the whole ecosystem, the whole lake. They can invest in collective prevention actions that reduce the chance of invasion for everyone. And if an invasion is already established, they can use collective control, maybe treating a larger area to reduce the overall invader population size, which then reduces damages for everyone in the next time period. Their goal is broader: maximize the total social welfare, discounted over the entire planning horizon.
Right, so you've got these two players, firms and the manager, making decisions simultaneously, potentially with different goals and timelines. And this, I think, is where the paper gets really fascinating. They use this integrated model to ask a fundamental question. Does actually capturing all these complex feedback loops between the biology and the economics really matter? Is it worth the effort? Or could we get away with simpler models where, say, the manager ignores what the firms are doing, or the firms ignore the underlying biology?
And the answer they find is a resounding yes, it absolutely matters. But it's nuanced. The finding is basically that these feedback loops are crucial, but the consequences of ignoring them biologically and economically really depend on the starting point, the initial conditions, and critically, how complete the manager's understanding or beliefs are.
Incomplete beliefs. Like assuming something that isn't true.
Exactly. Making decisions based on a flawed picture of reality, which, let's be honest, probably happens a lot in practice. And the paper shows this can lead to, well, pretty disastrous results.
They illustrated this with simulations, right, using examples based on their zebra mussel model where an invasion had already started.
Yes, let's look at one. Say you have a scenario where the manager ignores how the firms respond. The manager thinks, oh, the private companies will just adapt or control the mussels themselves. I don't need to worry.
Okay, so the manager holds this incomplete belief. What happens in the simulation?
Well, the manager basically stops investing in collective prevention and collective control. They think the private sector has it covered. The result: the probability of the invasion getting worse or spreading doesn't just creep up, it explodes something like 6 times higher in their model run. And the actual number of invaders, 20 times larger.
Wow.
Yeah. And overall welfare, the societal benefit, just plummets. Because the manager tried to free ride on private efforts that either didn't happen or weren't sufficient system-wide.
Okay, that's one feedback loop ignored. What about the other way around? What if the firm ignores the biological link? Maybe they just treat the muscle numbers as static.
Right, another simulation they ran. Here, the firm sees the mussels, assumes the population isn't really changing dynamically, and decides to control aggressively at a really high level. Maybe it seems cost-effective in their very narrow, static view.
So the firm is overspending on control based on bad biological assumptions.
Exactly. Now, the public manager sees this massive private spending on control and thinks, great, they're handling it. So the manager dials back collective prevention and control efforts to zero, effectively free-riding on the firm's overkill.
And the outcome?
Biologically, it's still bad. Because prevention is zero, the invasion probability and the overall mussel population nearly double compared to the optimal scenario. But interestingly, the welfare loss here isn't just from the increased mussels. It's significantly driven by the firm's hugely inefficient, overly expensive control efforts. They're wasting resources because they don't understand the population dynamics.
That's a powerful illustration. So the takeaway for you, listening, seems really clear. Ignoring these links is costly. Whether you're a manager assuming firms will fix it, or a firm ignoring the biology, or a manager ignoring the firm's potentially inefficient response, decisions based on these incomplete pictures lead to wasted money and much higher ecological risk.
Precisely. You really have to integrate the biological and economic systems. The paper makes a strong case that trying to manage them in isolation just doesn't work.
Okay, so feedback matters. Let's shift gears slightly and talk about the manager's mindset. This brings us to the second really interesting finding. How does the manager's personal tolerance for risk, how risk-averse they are, influence the choices they make between prevention and control?
This was one of the most, I think, counterintuitive results in the paper. You might expect a really cautious, risk-averse manager to double down on prevention, right? Stop the problem before it starts.
Yeah, that seems logical. Avoid the risk altogether.
But they found the opposite. Their models showed that more risk-averse managers tend to choose a strategy with less prevention and more control.
Less prevention. but more control. Why? That seems backward if you hate risk.
It does seem odd at first glance, but it boils down to the nature of the uncertainty associated with each strategy. Think about it from the manager's perspective. First, there's a direct effect of risk aversion. If I'm risk averse, I generally prefer a sure thing like holding onto a dollar over a risky investment where the payoff is uncertain.
Okay, and both prevention and control have uncertain payoffs, right? Their success isn't guaranteed. It depends on random factors like weather affecting muscle spawning or something.
Exactly. Both are risky investments compared to just keeping the money. However, and this is the crucial part, the degree of uncertainty in their effectiveness isn't the same. Think about control. Spending money to physically remove existing muscles right now, while there's some uncertainty, the link between spending and outcome is relatively clear. You spend X dollars, you can estimate pretty well how many muscles you'll remove. The marginal effect is less uncertain.
Okay, more predictable, more tangible maybe.
Right. Now think about prevention. Spending money to reduce the chance of an invasion happening next year or the year after. That outcome is inherently much more uncertain. Will the inspection program catch the one contaminated boat? Will the early detection system actually find the first few mussels?
Ah, I see. So for a manager who really dislikes uncertainty,
The dollar spent on control feels like a safer bet. Its immediate impact is more predictable, even if the long-term benefit of prevention could be much larger. Control offers more certainty in its marginal effectiveness right now.
and because prevention and control are seen as substitutes in the model, different ways to achieve the same goal of reducing overall damage.
Exactly, they act as technical substitutes. So the risk-averse manager, valuing certainty, shifts the portfolio. They trade away some of the highly uncertain long-term prevention investment.
For the more certain immediate payoff of control, it's like choosing the sure thing small win today over the potentially bigger but riskier win tomorrow.
That's a good way to put it. It's a kind of behavioral bias towards immediate tangible results driven by risk aversion.
And what's the consequence of this shift in the long run, according to the paper?
Well, it's not good for overall welfare. By underinvesting in prevention, you essentially delay the date when effective prevention measures might be implemented. This means the probability of invasion stays higher for longer, and if an invasion occurs, the population grows faster in those early periods because collective control was also potentially reduced in favor of firm-level control that might be less efficient.
So, the preference for short-term certainty leads to greater long-term risk and ultimately lower cumulative welfare over the whole planning period.
Precisely. The risk-averse choice, ironically, increases the overall ecological and economic risk down the road.
Okay, so let's try to synthesize this for everyone listening. What are the big takeaways from this deep dive into Finnoff and colleagues' paper? It seems like, first, this endogenous risk idea is really powerful. We can't treat invasive species management as just reacting to a biological problem. The economic decisions, the human behavior, the feedback loops between managers and private firms, you have to include them in the model. Or you risk making really bad, costly mistakes. Ignoring feedback leads to higher risks and wasted money.
Absolutely, that integration is key. And the second big takeaway is about the managers themselves. Their beliefs about how the system works, whether they account for feedback, are critical. And perhaps more subtly, their psychological traits, like risk aversion, can systematically push them towards strategies like favoring control over prevention that might feel safer in the short term but are actually worse for long-term ecological health and economic welfare.
Now, we should probably add the usual caveats. These specific numerical results, the six-fold increase in probability, etc., are tied to their specific model. It's based on zebra mussels in a particular type of lake system in the Midwest, so the exact percentages would likely change for different species or different environments.
That's a fair point. The results are definitely sensitive to the initial assumptions about the environment, the species biology, and how people perceive risks and costs. But the framework itself, the approach of integrating dynamic biology with endogenous risk economics, that's the really valuable contribution here. It's a blueprint that others can adapt.
Yeah, it opens doors for future research, right?
Yeah.
You could use this framework to explore other questions, like what happens if firms aren't so myopic? What if they do plan further ahead? Or how do different assumptions about the social discount rate, how much we value the future, change the optimal mix of prevention and control?
Exactly. It provides a powerful tool to keep exploring these really complex interactions.
Which leads us to maybe a final thought for you, the listener, to ponder. If this research suggests that managers, especially highly risk-averse ones, might have an inbuilt tendency to favor the short-term certainty of controlling existing problems over the uncertain long-term security of preventing future ones.
Then how should we, as a society, think about designing our environmental management institutions? How do we structure decision-making to counteract that potential bias? How do we ensure we don't consistently trade away long-term ecological stability for short-term relief, potentially leading to escalating risks and costs down the line? Something to think about.